in the summer of 1922. In a quiet office on the south side of New York City, a publisher named George Arthur Plimpton paid $10 for a piece of dirt. The man who sold it to him was Edgar Banks. Tall, sunburned, fedora pulled low, dust still clinging to the cuffs of his trousers, the kind of American who carried desert sand back from Iraq. Years later, novelists would borrow the life of Edgar Banks and use it to invent a fictional adventurer named Indiana Jones. But on that afternoon in Manhattan, Edgar Banks was simply a salesman. The object he had brought to sell measured 5 inches across and 3.5 inches tall, a flat slab of pale clay marked on both sides with hundreds of tiny wedge-shaped impressions arranged in 4 columns and 15 rows. Banks named a price. Plimpton paid him $10 and slid the slab into a drawer. Neither man knew what they had just traded. Neither man knew that the small chunk of fired earth in that drawer would, almost a century later, force 2 mathematicians on the other side of the world to write a sentence neither of them really wanted to publish. The sentence was this: the first true table of trigonometry was not Greek. It was older than Pythagoras by 1,200 years. Somebody in the city of Larsa, in the 2nd millennium before Christ, had already done the math, and the civilization that solved it would be erased, forgotten, and credited to the wrong people for 30 centuries. You are about to look at the most uncomfortable piece of clay in the history of mathematics. This is Plimpton 322. The tablet now lives at Columbia University, on the top floor of the Butler Library, inside a deep blue, velvet-lined display box. You can request to see it. You will need to wear gloves. You will need a librarian to bring it out of the climate-controlled vault. And then you can place it in front of you, exactly where George Plimpton placed it 90 years ago, and you can begin to count the marks. 4 columns, 15 rows. The left edge of the tablet is broken in a clean diagonal line. Small flecks of modern glue cling to the fracture. Somebody, somewhere in the 20th century, dropped this thing and tried to repair it before they understood what they were holding. The path the tablet took before it reached Plimpton's desk is mostly forgotten. We know it was pulled from a mound called Tell Senkereh in the south of present-day Iraq, sometime between 1919 and 1921, by men who were not archaeologists and who left no records. Tell Senkereh sits on top of the ruins of an ancient city named Larsa. Larsa was a center of mathematical learning during the old Babylonian period, roughly 4,000 years ago. It was sacked in 1762 BC by King Hammurabi of Babylon, and the small mud brick rooms where the scribes had once worked were buried under the dust of that defeat. Plimpton 322 dates to the 60-year window just before the sack. It is almost certainly the work of a Larsa scribe who never lived to see his city fall. The forensics that tell us this are surprisingly precise. Plimpton 322 is written in landscape orientation, with calculations running horizontally and a final column on the right labeled, in cuneiform, with the words its name. That formatting style, landscape, horizontal flow, that one specific column header, only appears in tablets from the kingdom of Larsa, only during the 60 years before Hammurabi's army arrived. Within that window, the tablet's writer had access to one of the most advanced mathematical educations on Earth. For almost a quarter of a century after Plimpton bought the tablet, nobody understood what it was. It sat at Columbia. It was cataloged. It was photographed. It was assigned the number 322 in a 1943 inventory by a scholar named Albert Mendelssohn, which is where its name comes from. And then in 1945, 2 men sat down with the photographs, and they cracked it open. Their names were Otto Neugebauer and Abraham Sachs. Neugebauer was a German-born historian of mathematics, working at Brown University. Sachs was an Assyriologist. Together they published a book called Mathematical Cuneiform Texts, and on page 38 of that book they did something that changed the history of mathematics. They translated Plimpton 322. They worked through the 4 columns. They identified the numbers as base 60 integers. Sexagesimal, the counting system the Babylonians used. And then they noticed that the 15 rows were not random. The 15 rows of Plimpton 322 are 15 Pythagorean triples. Each row gives you a right-angled triangle. The shorter side, the diagonal, and a complex ratio between the squares of the two. You can take any row, square the 2 numbers, add them, and the sum will equal the square of the 3rd number, exactly. 3,700 years before the calculation should have been possible. Somebody in Larsa had already done it 15 times, with no decimal approximations. With no rounding, you can see one of these rows yourself. If you ask Columbia for the photograph, row 11 of the tablet records a right triangle with a short side of 45 units and a diagonal of 75 units. Square those numbers. 2,025, 5,625. Take their difference. 3,600. The square root of 3,600 is 60. 3 sides, 45, 60, 75. A clean Pythagorean triangle. The Greek students of the 6th century before Christ would have called this the most basic right triangle relationship in the world. The man in Larsa worked it out before any Greek student was alive to be told, and he did not write down the cleanest example, the 3-4-5 triangle a child learns in school. He wrote down a less obvious one. He chose it for a reason. Neugebauer and Sachs did the careful, conservative thing. They called it a number theory exercise. A clever scribe, they said, working with what we today call a generating function, 2 parameters, p and q, plugged into a formula, producing exact integer triples. The interpretation was scholarly. It was sober. It assumed the Babylonians had been very good at arithmetic and slightly lucky at geometry. And for the next 70 years, that is what every textbook taught. Plimpton 322 was a Proto-Greek genius, a teaser for the Greek mathematics yet to come. But there is a problem with that story. The man you are taught to credit with right-angle geometry, the man whose name is fused into the theorem you learned in school, is Pythagoras of Samos. Pythagoras was born around 570 BC and died around 495 BC. Even if you give him the most generous possible birthday, even if you assume he wrote down the theorem the moment he came out of the womb, you cannot make Pythagoras older than Plimpton 322. Plimpton 322 is 1,200 years older. The Greek school of thought that named the theorem did not even exist when the clay was wet. So, why do you call it the Pythagorean theorem and not the Larsan theorem? Why is Pythagoras the household name and not whoever pressed these wedges into clay in 1800 BC? The answer is that the Babylonian record disappeared. The cuneiform script went silent around the 1st century AD. The libraries that held the tablets were buried, looted, or melted by river floods. The scribes who could read them died and took the language with them. For 1900 years, Europe did not know that Babylonian mathematics had ever existed. By the time cuneiform was decoded in the 1800s, the Greek narrative had already hardened. Pythagoras was the father of mathematics. The Mesopotamians were curiosities. A footnote, Plimpton 322 was a hole in that footnote. And in 2017, 2 mathematicians in Sydney decided to make it a much bigger hole. You need to meet them now. Daniel Mansfield, Norman Wildberger, both from the University of New South Wales in Sydney, Australia, both mathematicians, not historians, not Assyriologists. In August of 2017, they published a peer-reviewed paper in Historia Mathematica, Volume 44, pages 395 to 419. The title was 8 words long. Plimpton 322 is Babylonian exact sexagesimal trigonometry. The paper was about ratios. It was about a base 60 number system. It was about a clay tablet from Larsa and it was, in the words of its own authors, a 3,500-year-old version of the trigonometric tables that mathematicians had spent the last 2,000 years building from scratch. Their argument was strange and beautiful. The Babylonian system, they pointed out, used base 60 instead of base 10. 60 is divisible by 2, 3, 4, 5, 6, 10, 12, 15, 20, and 30. That is a brutal advantage. In base 10, when you try to express the ratio of the sides of a triangle, you get infinite decimals. 0.3333 forever. 0.142857, the sort of fractions that never resolve. In base 60, those same ratios snap shut. They become finite, exact, 3 or 4 digits, no remainder. So, when the scribe of Plimpton 322 wrote down the ratios of his 15 triangles, he did not approximate, he recorded the exact relationship. Each row perfect. Mansfield said on camera, in interview after interview, that this changed the history of mathematics. The Greeks did not invent trigonometry. The Babylonians did. 1,200 years before Pythagoras, 1,500 years before the Greek astronomer Hipparchus, who is traditionally given the title of father of trigonometry. Mansfield went further. He suggested the tablet was a working manual, a practical reference that Babylonian surveyors and architects would have used to plot fields, design temples, calculate the slope of a ziggurat. He held the tablet up to cameras. He posted videos. He went viral. For about 6 weeks in late 2017, the BBC, The Guardian, the New York Times, and every science magazine on earth ran the same headline. The Babylonians beat the Greeks. You should understand why this story was so seductive. Modern trigonometry, the kind you were taught in school, uses an angle, a circle, and the sine of that angle. It is built on the Greek model of a triangle that rotates around a single point. Every trigonometric value, every sine, every cosine is by its nature a finite slice of an infinite decimal. Even today, every scientific calculator you have ever held in your hands is somewhere deep inside rounding. Mansfield's claim was that the Babylonians, working in base 60, did not have to round. Their geometry was clean. Their tables were clean. And here, on a piece of fired clay smaller than a paperback book, was the proof. If true, that was not just an interesting historical footnote. It was a quiet accusation. It said that for 2,000 years, the version of mathematics the world adopted was, in one specific way, less precise than the version a Larsa schoolmaster threw together to drill his teenage students. And then the peer reviewers got their hands on it. You should know about a woman named Eleanor Robson. She is one of the world's leading Assyriologists. She works at the Cambridge Faculty of Asian and Middle Eastern Studies. She has spent her entire career inside the mathematical worlds of ancient Iraq, and 16 years before Mansfield's paper came out, in 2001, she had already published a piece in the very same journal, Historia Mathematica, titled Neither Sherlock Holmes Nor Babylon, a reassessment of Plimpton 322. The following year, she expanded it in the American Mathematical Monthly under the title Words and Pictures, New Light on Plimpton 322, 2 papers, both peer-reviewed, both, in retrospect, a slow demolition of the trigonometric reading before it was even published. Robson's argument is the harder one to swallow. She begins with a simple observation. The Babylonians, she points out, did not have a concept of angle. Not the way you have a concept of angle. They did not measure circles in degrees. They did not draw protractors. Their geometry was what scholars call cut and paste, physical, visual, area-based. They imagined rectangles being sliced and rearranged. They thought of squares being stretched. They did not think of triangles as fanning open from a single point of rotation. They thought of them as flat shapes with sides. So calling Plimpton 322 a trigonometry table, Robson said, is doing extreme violence to history. There could be no notion of measurable angle in the old Babylonian period. There could be no table of angles. There was no concept to record. What was Plimpton? 322 then. Robson's answer is colder and, in some ways, more astonishing. It was a teacher's reference, a master scribe in a Larsa schoolroom, training a generation of boys to handle land surveys and tax calculations, generated a list of 15 problems with clean, integer solutions, derived from a set of well-known reciprocal pairs. The tablet was a problem bank. It was the answer key behind the kind of exercise a student would be made to solve to prove he was ready to leave school and serve the kingdom. Plimpton 322 was not a working manual for engineers. It was a teacher's drawer. You have to understand what a reciprocal pair is to feel the weight of this. In base 60 arithmetic, certain pairs of numbers multiply together to give exactly 60, or to give 60 squared, or some clean power of 60. Babylonian scribes had memorized hundreds of these pairs. They were the multiplication tables of the ancient world, and a Larsa schoolmaster, sitting cross-legged with a fresh lump of wet clay, could generate the 15 rows of Plimpton 322 by walking through his memorized reciprocal pairs and writing out the right triangle that each pair produced. He did not need the concept of trigonometry. He needed the concept of a memorized list. The same way you, sitting in a 5th grade math class, did not need to invent the times tables. You just remembered them. And from those memorized tables, an entire universe of geometry could be derived without ever using the word angle. You do not lose the genius in this reading. You shift it. The Babylonians did not invent abstract trigonometry. They did something arguably stranger. They built a mathematical pedagogy so rigorous, so geometrically precise, so internally consistent, that one of its training documents, 3,700 years later, can still be read by working mathematicians as a complete and exact reference. The math, in other words, was real. The trigonometric framing was wrong. In 2018, a third voice joined the room. Duncan Melville, professor of mathematics at St. Lawrence University, looked at the tablet and pointed out that it gives you only the outputs of a calculation, the numbers. It does not show you the method. And because more than one method can produce the same outputs, assuming any particular method, including Mansfield and Wildberger's exact trigonometry, invites pure speculation. You can read the numbers honestly. You cannot honestly read the mind of the person who wrote them. The current consensus, as of the 2020 S, has settled. Plimpton 322 is one of the most sophisticated mathematical artifacts in human history. Its scribe was a genius. Its math is exact. The story that the Babylonians anticipated Greek trigonometry by 1,500 years, however, is no longer in the peer-reviewed scholarship. The story that survives is quieter and stranger and harder. The Babylonians built a mathematical culture so deep that the tools of their elementary education look to us like advanced geometry. We were not ahead of them. We caught up. You can see how deep it ran by looking at the tablets that lived next to Plimpton 322 in those same Larsa schoolrooms. There is one tablet at Yale University, catalog number YBC 7289, that looks like nothing. A small round disc of clay, the size of an apple, with a square scratched on the front, and a single number written along the diagonal. That number decoded is 1.414213. The square root of 2, calculated to 6 decimal places by a Babylonian student doing his homework. In our century, you need a calculator to match that precision. The student, 4,000 years ago, did it by hand. There is another tablet, Psi 427, from a site near Baghdad that records a property dispute. The scribe surveyed a field. He used right triangle geometry to mark out a perpendicular boundary so that 2 neighbors could split their land cleanly. He did this in 1900 BC. Daniel Mansfield, who studied the tablet in 2021, called it the oldest applied geometry in the world. These were not isolated incidents. This was a culture. The scribes of Larsa, of Babylon, of were trained from childhood to manipulate exact numerical relationships, the way you were trained to read sentences, and Plimpton 322 was their answer key. You should think about what you just heard. Plimpton 322 was made by a man whose name you will never know, in a city that was sacked 60 years after he wrote it, in a kingdom that the world spent 3,000 years forgetting. The clay was pulled out of the ground by smugglers. The smugglers sold it to Edgar Banks. Edgar Banks sold it to George Plimpton for $10. Plimpton kept it in a drawer until he died, and then he gave it to a university. The university stored it. The university cataloged it. And eventually, somebody understood what they were looking at. The library it lived in burned. The empire that built it collapsed. The civilization that replaced them forgot the tablet had been written. And then a man bought it for $10. And then another man in another century figured out what it said. And then a third group of people in our century argued for 2 decades about what it meant. And the clay, through all of it, kept its marks. 15 rows, 4 columns, exact. You can go and see Plimpton 322 in person. It is not behind glass. You can request the box. You can ask the Columbia librarian to bring it up. You can touch the table where it rests. The blue velvet is soft. The clay is dry. 3,700 years of dust have been brushed away from it, and what is left is 15 rows of small, careful wedges, pressed into the surface by a man working by oil light in a small room in the south of Iraq. This is the first record. There are 2 more coming.